Good morning, students. We'll start with the today's lecture. Uh, we have started with the chapter 4 stability analysis, and today is the last topic, right? Yesterday we have seen the numericals on difficulty 1 and difficulty 2, right? Then we have seen the application of Routh stability criteria for the linear feedback systems, means determine the range of k for stability, right? So for these range of values of k, system will be stable. That we have seen. The next last topic is relative stability analysis, right? Okay. Already we have differentiated between absolute stability and relative stability. Already I have introduced these terms: absolute stability and relative stability, right? Relative stability. Okay. In relative stability, already the system is stable. To what degree, to what extent the system is stable, means the depth of stability I can say. But here in absolute stability, the system is either stable or not unstable. That is very much clear cut. Yes or no answer will be there. But here it is in relative stability, the system is already stable, but to what extent, to what degree it is stable, right? And relative stability is inversely proportional to the real part of the roots, already I told, right? So the settling time in relative stability, it is inversely proportional to the real part of the roots. I'll explain you real part of the roots of the characteristic equation. You can take this. Okay, one of the root is lying here. For example, let me assume that the root is lying at -2, and let me assume this root is lying at -8. And you can observe here at -2, the pole is located. And let me assume that this is the response of the system, right? At when let me assume another pole is located at -8, and this is the response. You can observe the settling time, right? It is less here as compared to the settling time here. So TS settling time is more here, but as the real part of the root shifts far away from the imaginary axis, right? So the settling time goes on decreasing, means the system will try to achieve the final value or steady state value at the earliest. What is settling time? The settling time is that the time taken by the response to reach and stay within the allowable tolerance band of plus or minus 2% or plus or minus 5%. This we have seen, right? Okay. So the settling time goes on decreasing. Let me take another case. Let me take this as -10 plus j2, something like this. Okay, plus j5 minus j5. Then let me take this -40 plus j5 and minus j5. Okay, so this root is -10. Let me write it here: -10 plus j5 plus or minus j5. This one is -40 plus or minus j5. Okay, just observe these roots. Just observe only the real part of the root, -10 and -40. -40 is far away from this imaginary axis, so the settling time will be less. Here, if you take, the settling time is more, right? Here, the settling time is less. Is it fine? So, the settling time is inversely proportional to the real part of the roots. Means, here I'll say that the system is also stable, but this is less stable as compared to this one. This is less stable as compared to this is stable. So this is more stable as compared to this system, right? I hope you understood. So, and once again, this is less stable. Both are stable only, but as compared to this system, and this is more stable as compared to this system, right? Okay, I hope you understood. All the systems are stable because all the roots are lying in the left half of the S plane only, but the degree of stability, to what extent, to what depth the system is stable, that is okay. Is it fine? I hope you understood the relative stability. All right. Okay, we'll solve few numericals based on relative stability analysis. Yes, you know this. We know the nature of S plane. This is the real axis sigma, and this is the imaginary axis j omega, and this is the origin. Okay, fine. If all the roots lie in the left half of the S plane, this is left half of S plane, right? If all the roots lie in the left half of the S plane, the system is stable. If all the roots lie in the right half of S plane, the system is unstable. If the roots lie on the imaginary axis, then system is marginally stable. These things we know, right? Okay. Okay, let me, instead of this imaginary axis, let us shift this imaginary axis here, right? Maybe at -1, -2, let me call it as minus sigma 1. This sigma 1 can take values as 1, 2, 3, and so on. Means minus sigma 1, -1, -2, -3, -4, anything, right? So it is shifting towards left, right? Sigma 1 can take any values, -1, -2, -3 and so on, right? Okay, minus sigma 1. Let us shift this imaginary axis here to minus sigma 1 and let us call this new plane as z plane, alright? Okay, so the distance for the s plane, this is the imaginary axis of the s plane and this is the imaginary axis of the z plane, and this distance is sigma 1, right? But exact value is minus 6 because this is negative negative x-axis, right? Negative real axis, right? Is it fine? So it is minus sigma 1. The distance between the imaginary axis of the s plane and imaginary axis of z plane is sigma 1, right? Okay, so I will let us test whether all the roots are lying on the left half of z plane. If all the roots are lying on the left half of z plane, means it is as good as all the roots are lying in left half of s plane. But to what extent? Whether they are lying on left half of minus sigma 1. This sigma 1 can take any one value, -1, -2, -3. Let me assume that it is -2, and we will check the stability of the system whether all the roots are lying on left half of -2. -2 means, right? If the any of the roots are lying between 0 to -2, then system is okay. Whether it is relatively stable or not, that I have to check it. If I check whether the system is relatively stable, means for check for sigma equal to -2, if I say, then all the roots should lie on left half of z plane. The imaginary axis of the z plane should be at -2. So what we will do, for the normal characteristic equation will be given for s cube plus 2s square, something like this, s square plus s plus 1 equal to 0. So I want to shift this imaginary axis of s plane to z plane. So we will substitute s equal to z minus sigma 1 and we'll proceed and we'll get the modified new characteristic equation in terms of z. Okay, okay, we will get the modified characteristic equation and we will solve, and we will form the root array and root table, and we will observe the first column elements of the root array. So and we will judge whether the system is relatively stable based on the value of sigma 1 that is given. So we will have a look at the problem. We will try to understand this relative stability concept, right? Okay, we'll take this numerical. Check whether all the roots of the equation s cube plus 5s square plus 25s plus 30 equal to 0 have real parts more negative than -1. Try to observe here, more negative than -1 or not. It can be -2, -3, -4, -5, anything like that, because minus sigma 1 I told, no, right? Sigma can take any value, 1, 2, 3, 4. Here they are again more negative than -1. They can change the same problem. If they give -2, fine. -3 also fine. What they are asking, just I'll tell you, sigma j omega. This is the origin and this is s plane, and they are asking that whether all the roots have more negative than -1. Means let us shift this imaginary axis to -1 here. This is -1, right? Let me shift this here. So this is j omega. So this is -1. So this I will call it as z plane, and this is s plane, right? So now I want to check whether all the roots are lying on left half of z plane. Left half of z plane means whether all the roots are lying on left half of -1, right? I want to check this. Okay, if they are lying on left half of z plane, means all the roots in the first column of the root array, there should not be any sign changes, means the system is stable, right? Okay, any of the given system is stable only, but to what degree, to what extent, whether all the roots are lying on left half of -1 or 0 to -1, any roots are lying, that we have to check, right? Okay, we'll see one by one. Okay, put s is equal to what? Z minus sigma 1. Sigma 1 is -1 here, right? Don't take minus of -1. So it is -1 means z minus 1. You take it. Is it fine? Put s equal to z minus 1. Don't go by this z minus sigma 1, right? So sigma 1 minus sigma 1. This whatever the value they are given is minus sigma 1. So sigma 1 is 1. I hope you are getting. Don't get confused. Right? Sigma 1 is 1. So substitute z minus sigma 1. Sigma 1 is 1. Okay. So and get the modified characteristic equation. So replace s by z minus 1 everywhere. So z minus 1 whole cube plus 5 into z minus 1 whole square plus 25 into z minus 1 plus 30 equal to 0. Okay, we will solve it. So z minus 1 whole cube, a minus b whole cube formula you can apply, but let me apply this z minus 1 whole square into z minus 1 I will do, because a minus b whole square formula I know. Just z minus 1 I am doing like this, right? A minus b whole square, a square plus b square minus 2ab. I hope it's correct, right? a square plus b square minus 2ab, then into z minus 1. I am doing this first one, z minus 1 whole cube. Later on I'll substitute there, right? So let me multiply here, z cube plus z minus 2z square, then multiply by minus everything, minus z square minus 1 plus 2z. So what I will be getting, just I'll write it here, z cube I'll write here, then minus 2z square minus z square minus 3z square, then z plus 2z, 3z minus 1. Okay, I got this. The next plus 5 into z minus 1 whole square, already I have here. Z minus 1 whole square is nothing but a square plus b square minus 2ab, this one, right? Just multiply by 5. So I will multiply by 5 here because 5 is there. 5 into z square, 5z square, then minus 5 to z 10, minus 10z, then 5 1 ja 5, then this is 25 into z minus 1, 25z minus 25 plus 30 equal to 0. Is it fine? So we will separate out all the terms. Z cube, only one term is there, z cube. Z square terms, minus 3z square plus 5z square. Any other z square terms? No. 5 minus 3, 2, 2z square. Then 3z minus 10z, 25z. So let me add all these things. 25z minus 10z, 15z, right? 15z, 25 minus 10, 25 minus 10, it is 15. 15 plus 3, 18z. I hope it is correct, right? So if I am doing any mistake, please correct me, right? Because you will be more attentive. You can see that, right? Okay. Then constant terms, minus 1 plus 5. 5 minus 1, 4. 4, 4 plus 4. Then this both 4, 35, 30 minus 25, 5. 4 plus 5, 9. Is it fine? Correct? 9. So equal to 0. Now I got this modified characteristic equation. Modified characteristic equation. So earlier this original equation was corresponding to this S plane. Now one modified characteristic equation corresponds to this Z plane, right? Okay. So let us form the root array or root table, right? So we will form the root array or root table. Root array will form. Okay. So whether check all the powers of z are present, z cube, z square, z to the power of 1, z power 0. Yes, all the powers of z are present, no problem. Z cube, z square, z to the power of 1, z to the power of 0. Okay, 1 minute. Okay. So first we will fill up the odd term coefficients 1, 18. 1 and 18. Next even term coefficients 2 and 9. 2 and 9. 9 is the constant term, ticket, right? So only one term will be coming here. Just we will calculate this. What is that term? 18 2 into 18, open bracket, 2 into 18 minus 9 1 ja 9. 9 divided by 2. So I am getting 13.5 here. So only one element and this constant term will be coming here. Is it fine? Then observe the first column elements of the root array. All are positive, right? So what is the indication? If all the elements are positive, means the system has real parts. What are they asking? System has real parts more negative than minus 1, means all the roots are lying on the left half of z plane. Z plane, the shifted imaginary axis is at minus 1, means all the roots are lying in on left half of z plane, right? More negative than minus 1. So given system is, so given system is relatively stable, means simply stable also I can say, relatively stable, as all the roots are lying on left half of z plane, left half of z plane, means that is real parts are more negative than -1, that is having real parts more negative than -1. I hope you understood, right? I hope you understood. If any doubts, please unmute yourself and talk to me so that I can clarify your doubts. Next, we'll move to this example. Determine the range of values of k such that a characteristic equation s cube, and this characteristic equation has roots more negative than s equal to -1, means minus sigma 1 only, right? S equal to minus sigma 1, and here sigma 1 is 1, right? Sigma 1 is 1. Okay, here they are asking to determine the range here. Okay, we know how to determine the range, already we have seen yesterday, right? Application of root stability criteria for linear feedback control systems, that we have seen. Okay, so replace, see here, has roots more negative than s equal to -1, means they are asking for relative stability only. So replace s is equal to z minus sigma 1. What is sigma 1? It is 1, right? More negative, right? Z minus 1. So we'll form it. So z minus 1 whole cube plus 3 into k plus 1 into z minus 1 whole square plus 7k plus 5 into z minus 1, and this is the constant term, 4k plus 7 equal to 0. Okay, z minus 1 whole cube already we have done here. So here it is there, z cube minus 3z square plus 3z minus 1, right? Plus, okay, we'll multiply 3k plus 1 later on, right? 3 into k plus 1, right? So 3k plus 3 I'll multiply here with this, z minus 1 whole square, a square minus b square, I will write it later, a square plus b square, right? Plus b square minus 2ab. Minus 2ab means minus 2z, right? So a square plus b square I have left, so I will writing here a square plus b square minus 2ab, right? I have rearranged, that's all. The next, let me multiply with this, 7k plus 5. Let me multiply with this 7k plus 5. 1 minute, let me check it if I am doing proper or not. Is it fine? Okay, if it's fine, we'll proceed. Yes, this is fine. Let me multiply 7k plus 5 with z. 7k plus 5 into z. Okay, let me use the brackets for this so that it will be very clear, right? So let me use 7k plus 5 into z minus 7k minus 5, right? I am using the brackets properly so that I should not go wrong. Okay, let me separate out z square terms and all those things, right? So z cube minus 3z square plus 3z minus 1. Okay, let me multiply 3k plus 3 into z square, right? Or else let me multiply, okay, no problem, 3k plus 3 into z square. If anything I am making mistake, let me, yes, no problem. Just I am multiplying this minus 2z. Z terms one side I have to take. So let me multiply 2 for this. 2 3 just 6. Or else what shall I do? 2z into this I have to do. So okay, let me, no problem, or let me expand it. 3k plus 3 plus 1 into this, it is 3k plus 3. 7k plus 5z, I will keep it as it is. 7k plus 5 into z. This minus 7k minus 4k. So how much I will get? 7 minus 4, 3. 3k. Is it fine? This both I have done. Then 7 minus 5. This one, 7 minus 5, it is 2, equal to 0. So let me separate out the terms. Z cube, fine. This is fine. Z square terms, let me underline it. Z square terms. This is Z square. Where is Z square? Any other terms? Right. Only this much, right? Okay. Yes, you can observe here minus 3z square. If I multiply, what I will be getting? Let me do it here only. Rough work. So I'll write it. I'll take some space here. So what I'll be getting? 3k z square plus 3z square I will be getting from this. 3k z square plus 3z square. So for 3z square and 3z square will get cancelled. So what I will be getting? 3k z square. Is it fine? 3k z square. Next, z terms will separate out. Z terms. This is z term. This is also z term. Okay. Okay, z terms this one. So let me expand this. Minus 2 3 just 6 kz. 6 kz. Right? Minus 3 2 just 6 kz. Minus into plus minus 2 3 just 6z. Then next, here it is there. 7 kz. Is it fine? Plus 5z. So these are the z terms. So 3z minus 6z means minus 3z, right? Okay. 3 minus 6 plus 3. So minus 3z. Minus 3z plus 5z. How much? 5 minus 3. Minus 3. 5 minus 3 is 2z. So I am getting 2z from this. The next, as k is there. Let me check it. So 3k, sorry, I have done something wrong. This I should not take. So sorry, this is already over. So 3z minus 6z minus 3z plus 5z, 2z, fine. Then this is over already. This one, 7kz minus 7 minus 6 means 1 kz plus kz, right? So let me take out z and write it, z outside. So 2 plus k or k plus 2, k plus 2 into z, right? K plus 2, take it, right? Okay, this is over. Then constant term, we will have a look at it. So let me change the ink color so that it will be help us. Minus 1, this is covered, this is covered, this one is there, and this one is there. Okay, we will cover all these things. So 3k 3k they will get cancelled. 3 plus 2 5, 5 minus 1 4. I hope it's correct, right? Final equation is correct. Z cube plus 3k z square plus z into k plus 2 plus 4 equal to 0. This is the modified characteristic equation in terms of z. So do it carefully, you should not go wrong. Modified characteristic equation. So now we will form the root array for this. Just observe all the powers of z are present. 3, 2, 1. Yes, all the powers of z are present. So we will go to the next slide and form the root array. So z cube, it is starting from z cube, z square, z to the power of 1. 1 minute. Okay, fine. Z to the power of 1, z to the power of 0. Okay, 1 k plus 2. 1 k plus 2. I am writing the terms here, right? Odd term coefficients 1 and k plus 2 over. Next, even term coefficients is 3k and 4. 3k and 4. 4 is the constant term, right? 4 is the constant term. So just tick it mark. Okay, two elements. So next only one element will be coming here, right? So 3k into k plus 2 minus 4 on the 4 divided by 3k. This one element I am calculated. Next, this element just no need to calculate. This constant term it will be coming here. Okay, what they are asking, whether all the roots are more negative than s equal to minus 1 means, right? Okay, just observe the first column elements of the root array, right? So if all the roots has to be more negative than -1 means all they should be greater than 0, right? So any of 1 is greater than 0. First we'll take this condition. 3k is greater than 0. So which implies that k is greater than 0. This is one condition. Next we'll take up this. So 3k into k plus 2 minus 4 divided by 3k is greater than 0. But divided by 3k, if it goes that side, this will vanish. So I'll just only take this 3k into k plus 2 minus 4 is greater than 0. We'll put the condition for this because this is greater than 0, right? Okay, 3k into k plus 2 minus 4 is greater than 0. Let us see what is conditions will come here. 3k square plus 2 3 just 6k minus 4 is greater than 0. So we'll see the conditions. We will solve the roots of this and we will calculate the conditions for k. So I'll go to equation degree, second degree. So a is 3, b is 6, c is -4. So k value what I am getting here is 0.527. K what I am getting just I'll write 0.527 and another value I am getting minus 2.527. So if I calculate these roots, I will be getting these two values, right? So k should be greater than 0, I told, no, right? If I calculate this, so k should be greater than 0.527 or k should be greater than this. Two conditions I am getting. So k is greater than 0.527 or k is greater than, right? If I calculate, right? I hope you are getting, you have calculated the roots. These are the roots of, right? Okay, k is greater than minus 2.527. Which one is valid? So it is always k is greater than 0.527. So I will take this, not this one. Because if k is greater than minus 2.57 means it includes the values from minus 0.25, 2.527 to 0.527. If I take this k is greater than 0.527, these values from minus 2.527 to these are invalid. So we will take this k is greater than this one condition and this is another condition, right? From this we got this condition k greater than 0. From this we are getting k is greater than 0.527, right? These are the two conditions. I hope you are getting, right? 0.527. Okay, but k greater than 0, the condition vanish, right? So k greater than 0 or k greater than point. So I'll be taking this only. So I'll put the range of values of k should be greater than what? Greater than 0 or greater than 0.527. It is greater than 0.527, but it should be less than infinity. K is greater than 0.527, but it is less than infinity. This should be the range of values of k for the system to be relatively stable. For the system to be relatively stable. To have roots more negative than -1. More negative, right? More negative than s equal to -1. More negative than s equal to -1. I hope you are getting this. If any doubts, you can ask here, right? So I am not choosing k greater than 0. I am choosing k greater than 0.527, right? Always. So 0 to 0.527 values are discarded after 5.52. So k should be greater than 0.527, but less than infinity is the range for the system to be relatively stable or to have the roots more negative than s equal to -1. Is it fine? Okay. So this is the range of k we have found out. Then next, okay, this actually this chapter is over. So I will take up the next chapter, but before going for the next chapters, we will be solving few more numericals, right? This chapter is complete now, right? So we'll be solving few more numericals, right? Okay. For a system with a characteristic equation s power 6, 3s power 5, this examine the stability. Observe here whether all the powers of s are present. 6, 5, 4, 3, 2, 1, 0. Yes, all are present here. Okay. You can solve it, but let me solve it. Okay, all the powers of s are present. Let me form the root array or root table. Or table, one and the same, right? So s power 6, 5, 4, 3, 2, 1, 0. And we came to know that all the powers of S are present: 6, 5, 4, 3, 2, 1, 0. None of the coefficients are missing and none of the powers of S are missing here. So odd term coefficients 1, 4, 5, 2. 1, 4, 5, 2. 2 is the constant term, mark it, right? Then even term coefficients 3, 6 and 3. Yes. Next we'll calculate for 3 elements, next 3 elements, right? 3, 6, 3 over. Next we'll calculate this element. 4 3 is 12. 12 minus 6. 6 by 3. So it is 2. 6 by 3 it is 2, right? 4 3 is 12, right? 12 minus 6. 6 by 3. So 6 by 3 is 2. Next calculate this element. So observe here. So 3 elements, fine. Okay, we'll calculate this. Leave this 5 3 is 15 minus 3 1 is 3. So 12 I am getting divided by 3. So I am getting 4 here. No need to calculate this. This is constant term. It will come here 2. Right? The next 3 elements. Next 2 elements will be coming here. So I will calculate that. So 6 2 is 12 minus 4 3 is 12. 12 means 0 I am getting here. Then next we will try to calculate this element. So leave this above column. So 3 2 is 6. 3 2 is 6. So I am getting 0. Means this is row of zeros is coming. So row of zeros. Row of zeros. Row of zeros means difficulty 2, right? Yes, difficulty 2 means system. It indicates, what does it indicate? Indicates the presence of pair of symmetrically located roots. This is one thing. And system can be either unstable or marginally stable. Unstable or marginally stable. But it cannot be stable. This is sure, because difficulty 2 outcome means it indicates the presence of pair of symmetrically located roots, and system can be either unstable or marginally stable, these two things. So we'll form the auxiliary equation. So A of S, so we'll just make use of the rows just above the row of zeros. 2s power 4 plus 4s square plus 2 into s power 0. This is the auxiliary equation. Take derivative of this. To fill up the coefficients of s cube row, take the derivative. So 4 2 is 8, 8s cube plus 4 2 is 8s. Okay, 8 and 8 are the coefficients. So we will fill up 8 and 8 and we'll continue. So I'll go to the next slide. S power 6, 5, 4, 3, 2, 1, 0. One 4 5 2. 3 6 3. Then 2 4 2. Yes, what are the coefficients of this s cube row? It is 0 0, right? Here we have found out that coefficient here. Let me write it here. Coefficient of s cube row. S cube row is 8 comma 8. Right? The coefficients of this derivative 8 comma 8. So let me write it here. 8 comma 8. So 3 elements. Okay, this is the constant term 2. Let me mark it here like this for our convenience, right? Okay. The next 2 elements will be coming, out of which constant term will come here. This is fine. So we want to calculate this element. Okay. 4 8 32. 8 into 4 open bracket 8 into 4 minus 8 into 4 minus 8 into 2 16 divided by 8. So I am getting 2 here. Is it fine? Next 2 elements. Next 1 element will be coming here. So what is that 1 element? 2 edges 16, 2 edges means once again I am getting 0 here, right? So you can observe here these 2 elements, only 1 element. This is difficulty 1 because only 1 element, right? there are no other elements. So this is the only one element. So that first element in the first column of the root array 0 means this is difficulty 1. So difficulty 1. So in the same problem, I am getting both difficulty 2 as well as difficulty 1. So what we have to do? Replace this 0 by the small positive constant epsilon. That would be better, right? So I'll change the ink color and proceed. So I will replace this 0 with epsilon, the small positive number. Epsilon is a small positive number. A small positive number. And epsilon is almost tending towards 0. So these two conditions, right? So I substituted epsilon is a small positive number. And here, yes, this is constant. Anyway, it will be constant here. This will be calculated, right? Okay. No need to calculate this. If you calculate also, you will get the same thing, right? Okay, fine. Next, you can observe here. You will not observe the elements of the first column of the root array because already difficulty 2 and difficulty 1 are coming means system cannot be stable. That is for sure, right? So whenever I am getting this difficulty 1 and difficulty 2, I am very much sure that system cannot be stable. It can be either unstable or marginally stable. So I will solve the roots of the auxiliary polynomial. So auxiliary polynomial is a of s. Let me write it here. A of s is equal to 2s power 4 plus 4s square plus 2 equal to 0. So this is the auxiliary polynomial. You will solve the roots of this. So these are the dominant roots. They will get the stability of the system. So let me solve this. So this will be s power 4 divided throughout by 2, right? 2s square plus 1 equal to 0. Is it fine? Yes, I can divide throughout by 2, right? 2 1 2, 2 2 4, 2 1 2, right? Then put x is equal to s square. So this equation is x square plus 2x plus 1. We will solve the roots of this. Is it fine? So equation second degree. So value of this is 1, a is 1, b is 2, c is 1. So I am getting the roots as x is equal to minus 1 is one root, at another root is, sorry, 1 minute, minus 1, minus 1, minus 1 only, right? So two roots I am getting. Okay, let me shift my calci to normal mode. Okay, fine. So what is x? X is nothing but your s square. S square equal to minus 1, s square equal to minus 1. So what I am getting? So first two roots 1 comma 2 plus or minus j. Then third comma fourth root, that also plus or minus j. So here you can locate the roots here on the s plane. So plus or minus j, plus j minus j, one set of roots, and same another set of roots are lying there only. Oh, they are overlapping. Plus j minus j. So repeated roots are there on the imaginary axis. So given system is unstable. Repeated roots on imaginary axis are j omega axis. So given system is unstable. So given system is unstable. I hope you understood. The same problem we came across difficulty 2 and difficulty 1, right? So I have written the answer here. Unstable, the roots are plus or minus j, plus or minus j. We have found out, right? The next, we'll take up this numerical. So this chapter is over. Just we are solving the variety of problems. That's all, right? A unity, okay, 1 minute. A unity negative feedback control system has an open loop transfer function consisting of, observe here, it consists of two poles, two zeros and variable gain k. The zeros are located at minus 2 and minus 1 and poles are located at 0.1 and plus 1. Using Routh stability criterion, determine the range of values of k for which the closed loop system has 0, 1 or 2 poles in the right half of S plane. Yes, they have not given the open loop transfer function. We have to construct here. So they are telling zeros are located at minus 2 and minus 1 means what I will be getting here in the numerator, s plus 2 into s plus 1, and variable gain will be coming in the numerator k. I have to form the open loop transfer function. divided by this numerator. Equate the numerator to 0, I will be getting s equal to minus 2 and s equal to minus 1. So minus 2 minus 1, these are the zeros. The numerator term will give me the zeros, right? Right? So we have to frame the open loop transfer function here, and poles are located at this. So s minus 0.1, because 0.1, right? S minus 1. Equate the denominator to 0, you will get the poles. S equal to s minus 0.1 equal to 0 means s equal to 0.1, and s minus 1 equal to s equal to plus 1. These are the poles. So this is the open loop transfer function. We have to frame it, right? Just by reading this, we have to frame it. Open loop transfer function. Next, so we have to form the characteristic equation. Anyhow, it is the unity negative feedback system. H of s is 1. So 1 plus g of s into h of s is 1. 1 plus g of s equal to 0 is the characteristic equation, general characteristic equation, right? So we'll form this 1 plus k into s plus 2 into s plus 1 divided by s minus 0.1 into s plus 1 equal to 0. So we'll get the characteristic equation first. So we'll take LCM, right? So if I take this one LCM, it will go this side and it will be 0. So just multiply s into s square plus s into 1 1s minus 0.1 s 1 into 0.1, so minus 0.1. Is it fine? 0.1 into this is over, plus we'll multiply this k, we will keep it separate outside. Let me multiply here s plus 2 into s plus 1. I am writing here. I will multiply and write it here. So s into s square plus s plus 2s plus 2 1 2, right? Is it correct? S square plus s plus 2s plus 2. So let me multiply ks. So I will multiply k for this. Ks square plus 2s plus s, 3s, right? So 3ks plus 2k equal to 0. So we'll separate out the s square terms one side. So we take s square outside. So what I will be getting? K plus 1 or 1 plus k, whatever it is. K plus 1. Then s terms you separate it one side. Yes, tell me.
Sorry.
Yes.
G of s is s minus 1, sir.
G of s. Yeah, sorry. Yes, thank you very much. ಹೌದು, ಇದು s minus 1 ಇದೆ. Yes, thank you very much. ಯಾರಿದು?
Vinayak, sir.
ವಿನಾಯಕ್, ವೆರಿ ಗುಡ್. ಥ್ಯಾಂಕ್ ಯು ವಿನಾಯಕ್. ಇಲ್ಲಾಂದ್ರೆ ಮುಂದೆ ಎಲ್ಲ ತಪ್ಪಾಗ್ಬಿಡ್ತಾ ಇತ್ತು. ಕರೆಕ್ಟ್. ಎಸ್
Yes.
ಮೈನಸ್ ಮುಂದೆ ಎಲ್ಲ ಪ್ರಾಬ್ಲಮ್ ತಪ್ಪಾಗ್ಬಿಡುತ್ತೆ. ಥ್ಯಾಂಕ್ ಯು. ಇಲ್ಲಿ ಏನು ತಪ್ಪು ಮಾಡಿದೆ ನೋಡ್ಬೇಕು ಈಗ. ನೋಡೋಣ. ಎಸ್ ಇಂಟು ಎಸ್ ಫೈನ್. ಇಲ್ಲಿ minus 1 ಬರ್ಬೇಕಲ್ಲ. ಎಸ್ ಸ್ಕ್ವೇರ್ ಮೈನಸ್ ಎಸ್, ಇದು ಮೈನಸ್ ಎಸ್ ಆಗುತ್ತೆ. ಎಸ್ ಸ್ಕ್ವೇರ್ ಮೈನಸ್ ಎಸ್, ಇದು minus 0.1 ಎಸ್ ಕರೆಕ್ಟ್ ಇದೆ. ಮೈನಸ್ ಇಂಟು ಮೈನಸ್ ಪ್ಲಸ್ ಆಗುತ್ತೆ. ಪ್ಲಸ್ 0.1 ಮೈನಸ್ ಇಂಟು ಮೈನಸ್ ಪ್ಲಸ್, ಇದು ಕರೆಕ್ಟ್ ಆಯ್ತು. ಡಿನಾಮಿನೇಟರ್, ಇದು ನ್ಯೂಮರೇಟರ್ ಕರೆಕ್ಟ್ ಇದೆ, ಏನು ಪ್ರಾಬ್ಲಮ್ ಇಲ್ಲ. ಥ್ಯಾಂಕ್ ಯು ವಿನಾಯಕ್. ಓಕೆ ಫೈನ್.
Yes, sir.
ಥ್ಯಾಂಕ್ ಯು. ಕಂಟಿನ್ಯೂ ಮಾಡೋಣ. ಎಸ್ ಸ್ಕ್ವೇರ್ 1k ಪ್ಲಸ್ 1. ಆಮೇಲೆ ಎಸ್ ಟರ್ಮ್ಸ್ ಸಪ್ರೇಟ್ ಮಾಡೋಣ. ಇದು ಮೈನಸ್ ಎಸ್, ಇದು ಆಮೇಲೆ ಇದು. ಓಕೆ. ಮೈನಸ್ ಎಸ್ ಮೈನಸ್ 0.1, ರೈಟ್? minus 1 minus 0.1. ಸೊ minus 1 minus 0.1. ಸೊ minus 1.1 ಎಸ್ ಆಗುತ್ತೆ. minus 1.1 ಎಸ್ ಇವೆರಡು ಸೇರಿ minus 1.1 ಎಸ್, ರೈಟ್? ಆಮೇಲೆ ಇನ್ನೊಂದು 3 plus 3ks. ಸೊ ಎಸ್ ಕಾಮನ್ ತೆಗೆದುಬಿಡೋಣ. ಸೊ ವಾಟ್ ಐ ವಿಲ್ ಬಿ ಗೆಟಿಂಗ್? 3k. ಏನಾದರೂ ತಪ್ಪಾಗಿದೆ ನಾವು ನೋಡ್ಬೇಕು ಅಮ್ಮ. ಕರೆಕ್ಟ್ ಇದೆ ಅನ್ಸುತ್ತೆ, ಏನು ಪ್ರಾಬ್ಲಮ್ ಇಲ್ಲ. ವಿ ಕ್ಯಾನ್ ಪ್ರೊಸೀಡ್ ಅನ್ಸುತ್ತೆ. ಎಸ್, ವಿಲ್ ಪ್ರೊಸೀಡ್, ನೋ ಪ್ರಾಬ್ಲಮ್, ರೈಟ್? minus 1 minus 1.1 ಎಸ್ ಕರೆಕ್ಟ್ ಇದೆ. 3k ಎಸ್ ಕರೆಕ್ಟ್ ಇದೆ. ವಿಲ್ ಟೇಕ್ ಎಸ್ ಕಾಮನ್ ಫ್ರಮ್ ದಿಸ್. 3k minus 1.1. ಸೊ ವಿಲ್ ರೈಟ್ ಇಟ್ ಹಿಯರ್. ಎಸ್ ಇಂಟು 3k minus 1.1. ಉಳಿದಿದ್ದು ಕರೆಕ್ಟ್ ಇದೆ ಅನ್ಸುತ್ತಲ್ಲ, ಏನು ತಪ್ಪಿಲ್ಲ ಅನ್ಸುತ್ತೆ. ಉಳಿದಿದ್ದು ಫೈನ್. ಓಕೆ. Yes, okay. 3k minus 1.1. Then next, I will change the ink color better. A constant term 0.1 2k ಇದೆ. So let me write it as 2k plus 0.1. This is constant term. Okay. Then we will form the root array, right? So let me rewrite it once again. S square into k plus 1 plus s into 3k plus s into 3k minus 1.1 plus 2k plus 0.1 equal to 0. Yes. What they are asking, using root stability criteria, determine the range of values of k for which the closed loop system has zero poles in the right of one by one will take zero poles in the right of S plane, means there should not be any poles in the right of, that is one condition. Another one is only one pole should be in the right of S plane. Third is two poles should be in the, we will take this condition later after forming the root array. First we will form the root array. All the powers of S are present, s square, s to the power of 0. Is it fine? Okay. So s square, s to the power of 1, s to the power of 0. So first we'll write on the odd term coefficients k plus 1. Next constant term is 2k plus 0.1. So this is the constant term. Next we'll write the even term coefficients 3k minus 1.1. That's all, right? I don't have any other term. Then constant term will be coming here, L shape, right? 2k plus 0.1. Okay, this root array is formed now. Okay, so we have to observe the first column elements of the root array. We have to observe this, all these first column elements of the root array. And always this a naught term means this is always greater than 0. This is always right. So let me put the condition for the system to be stable. For stability, let me write it here. For stability, always this first term k plus 1 should be greater than 0. This is always first term. The next all should be positive, right? This is greater than 0, that means it will be stable, then only system will be stable. 3k minus 1.1 is greater than 0, then 2k plus 0.1 is greater than 0 for the system to be stable. But what they are asking, observe here, for the system, right, you determine the range of values for which the closed loop system has zero poles in the right of S plane. So there should not be any poles in the right of S plane, sigma plus j omega. So when there should not be any zero poles in the right of S plane, means the system should be stable, means all the poles should lie in the left of S plane. So first elements in the first column of the root array should be greater than 0. So these conditions, whatever I have written, this is greater than 0, this is correct. So we will calculate the range of values of k, right? So 0 poles, first condition we will take it for 0 poles in right of S plane, 0 poles in right of S plane. We'll consider this condition, 0 poles in right of S plane, right? Okay, means all should be greater than 0. This element should be greater than 0, this element, means all should be positive. So we'll find out the condition here. So from this what I will be getting, k should be greater than minus 1, right? Take this one this side, k should be greater than minus 1. From this what I will be getting, 3k should be greater than 1.1, which implies k should be greater than 1.1 divided by 3. We'll see 1.1 divided by 3, so 0.36, right? The next from this what I will be getting, 2k should be greater than 0.1, which implies k should be greater than 0.1 by 2, 0.1 divided by 2, so 0.05. So what should be the range of values of k? For this I will tell you one trick here. Just let me, this is not the actual one, but let me tell it as a trick, right? So this is 0. So here k should be greater than minus 1. Minus 1 is coming here, right? K should be greater than minus 1. Greater than minus 1, right? Greater than minus 1 means it is like this. Just this is my thumb rule, what I am analyzing. The next, k should be greater than, next two values are there, 0.05. Let me look at 0.05 here, 0.05. Another value is 0.36. Let me look at here, 0.36. So second condition, k should be greater than 0.36. So k should be greater than 0.36. Then k should be greater than 0.05. K should be greater than point, right? Observe here. So k greater than minus 1 is not valid. K, so k should be greater than, So k should lie between, this is the range, this should be the range, k should be greater than 0.6. So observe here, k should be greater than 0.36 but less than infinity. I hope you are getting what I am telling. So k should be greater than this, greater than this. So finally I will tell that k should be greater than 0.36 but less than infinity. This is the range of values of k, so that the zero poles will be in the right half of S plane. I hope you are getting this. Yes. K should be greater, they are only to given. Actually, k is greater than zero point 0.3. What I am getting here is 0.36. 1 minute. Yes, 0.36. But it should be less than infinity. Right? So this is correct. I hope you are understanding. The next
Sir,
second. Yes, tell me. Tell me.
sir, k should be greater than minus 0.05.
Minus 0.05. Why it is minus 0.05?
So because when you transfer 0.1 to the other side, it should be negative.
Here I have done once again mistake. Let me check. Oh, here it is. 1 minute. 1 minute. Okay. Minus 0.1. Okay, fine. 1 minute. Yes. Thank you. 1 minute. Let me correct it once again. K should be greater than minus 0.05, right?
Yes, sir.
Minus 0.05. Yes. Okay. Minus 0.0. Let me. Minus 0.05 means here it will come. Minus 0.05. So greater than this. But here it is not affecting. Anyhow, it is greater than. Okay. Fine. So K should be greater than minus 0.05. So this will not come. But finally, K should be greater than 0.36 but less than infinity. This condition holds good. Right? But I have done a mistake here while calculating. I do agree. But this range of K remains the same. Right? Okay. Zero poles. Next, we will take one pole should be in the right half of S plane. Second condition. One pole. Second one pole should be in one pole in right half of S plane. So what they are telling, sigma j omega, only one pole should be in the right half of S plane. This is right half of S plane. Only one pole means one sign change should be there. When the one sign change will come, we will see these elements k plus 1. I will write this first column elements k plus 1. This is always positive. The next 3k minus 1.1. Let me put the condition later. 2k plus 0.1. Okay, these are the first column elements I have written. So only one of the elements should be in the right half of S, one sign change. So this is always positive, first one. So let me take this one also as positive. Let me take this as negative. Positive means this is greater than 0, this is greater than 0, but this is less than 0. So then only it will be negative. Number of sign changes is 1. Number of sign changes means one pole is lying in the right half of S plane, right? This I will be following. So this already I have done. What I am getting, this greater than 0 pole condition, k is greater than, no need to calculate. Once k is greater than minus 1, from this second one 3k, sorry, k is greater than 0.36, this k is greater than 0.36. Only this one 2k is less than 0 and means k should be less than, k should be less than minus 0.05. I hope you are getting what I am doing. This is greater than 0. Now it had become less than 0. Just make it less. So k is less than minus 0.05. These are the range of k. So let me use the thumb rule. Actually, this is not the strict one. Just in order to find out the range. So let me, minus 0.05 is here. Minus 0.05. Minus 1 is here. Then 0.36 is here. So k is greater than minus 1. Greater than means it will go right side like this. Greater than. K is greater than 0.36 means once again it will go right side only. But k is less than 0.05. Observe here. This is the beauty. Yes, k is less than. So this is the shaded area. So value of k should lie between this. So k should be lying between. So minus 1 greater than minus 1 but less than minus 0.05. K should be greater than minus 1 but less than minus 0.05. This is the range of k. So that one pole will be in the right half of the S plane. I hope you have understood. If any doubts, you can minus 1 to 0.05. They are written here, right? Minus 1 to 0.05, right? Then third, if any doubts, you can ask. Okay, third one, can you do it? Third one, two poles in the right half of S plane. Two poles in the right half of S plane. Two poles in right half of S plane. Two poles should be in right half of S plane means two sign changes should come. So let me write the first column elements once again. K plus 1. This is always positive. 3k minus 1.1. 2k plus 0.1. So two sign changes means plus 2, this I will make it negative. Once again I will make it positive. Plus 2 minus 1 sign change, minus 2 plus 1 more sign change. Plus 1 plus 1. I hope you are getting two sign change means two poles will be lying in right half. So this is positive means this should be greater than 0. This is negative means this is less than 0. Once again this is greater than 0. So you'll take this is greater than 0 means what I will be getting from this, k is greater than minus 1. I am referring to this previous one. This is less than 0 means k should be less than 0.36. Here this is greater than 0. So k should be greater than minus 0.05. I am referring to this and writing, right? It was less than 0, now it is greater than 0, right? The same thing. So what is the range of k? Can anyone tell? What is the range of k? By looking at all these values, what is the range of k? Can anyone tell? This thumb rule I told already. Plot it. So 0 is here. So minus 0.05, minus 0.05, then minus 1, then 0.36 will come here. So k is greater than minus 1, k is less than 0.36, but k is greater than minus 0.0. So this is the range of k. K should be lying between minus 0.05 but less than 0.36. This is the range of k, so that two poles will be in the right hand, right half of S plane, 0.05 to 0.36, right? 0.05 to 0.36. I hope you are getting. Doubts is cleared?
Yes, sir.
Okay, fine. The next, last one. Maybe I will be solving this. Next one I will assign you, right? Okay. Already 11. I hope there is next class is not there. Can I extend for another 5 minutes, 5 to 10 minutes?
So next class is there, sir.
Sir, we have another class, sir.
Which one?
HDL, sir.
Sir, HDL.
They have, okay. Actually, I am having only this problem and another one is homework for you people. You take this homework. Okay, later on I will leave this. Or else you take this also. I will be giving the solution. Take this as homework. Both you take it as homework. Let me take, okay, I'll stop recording.